Good evening. Today we are going to see the design of ground beam that is simply supported. So simply supported ground beams. So now try to understand the difference between ground beams and plinth beams. So these beams may be at same level, or if our floor level is above the ground level, in that case, whatever outside beams we have, suppose we have plan in this fashion, then whatever outside beams we have, these beams will be as ground beams, and whatever inside beams we have, which is these beams, so these beams will be designed as plinth beams. So try to understand, if we have ground level and after that we are going to be ground level or floor level we have same, then in that case we can have ground beam and plinth beam at same level. Otherwise we have ground beam at ground level, then we have 300 to 400 mm height of the plinth, and then we have at floor level we have these plinth beams. So now we will go to ground beam. Design a ground beam to carry 230 mm thick and 300 mm height brick masonry wall. The effective span of the beam is 4 meter. Now here directly effective span is given, and it is simply supported at ends. Use M20 and Fe415. Unit weight of masonry is 19 kilonewton per meter cube. It may be 18, it may be 20. Here it is given as 19. Now steps we have same effective span, L effective. Now in this we are going to consider L effective, that is 4000 mm as it is given. Then we have to go for trial depth. Now in slabs we are going to use L effective upon D is equal to basic L by D ratio into modification factor. But here we will not go for this, because from this we are going to get depth less, and that depth will not satisfy your deflection, your moment criteria. In case of beams, if we will see, we have D is equal to under root of mu upon Ru into B, and in slabs we have B as 1000 mm. So by using this, our depth for moment will be less than this. But in case of beams, this B is 230 or 250 or 300, and in that case this criteria will not be satisfied, and therefore value of D in beams is taken as L effective upon 12 to L effective upon 18. So now here we have considered actually D is equal to L effective upon 15, 4000 upon 15, which will be 266.767 mm. Already I mentioned we are going to consider that effective depth, the the overall depth equal to effective depth plus D dash. In beams, this generally is taken as 40. Clear cover is taken as to 30, and 5 by 2 20 mm is generally considered, so 20 by 2 10. So we have to keep in mind, in slabs we have 20, in beams we have 40, in columns we have 40, and in footing we have 50. So 266.67 plus 40, it comes 306.67 millimeters. So we will provide overall depth as 310 millimeter and effective depth, that is 270 millimeters. Now we have next step, load calculations. So we have only two loads. One is weight of wall and second is self weight of beam. Now weight of wall we have, that is 19 into B into H. We are going to find out in kilonewton per meter. We have three dimensions for beam wall. So if we will consider this wall, so we have wall in this fashion. So we have three dimensions for it. And as we are going to find out, we have beam like this below this, and therefore we are going to find out that value by multiplying height and by multiplying width. So automatically we are going to get unit your UDL on span of beam, and therefore we have multiplied by B and H. So 0.23 into 3, we will get 31.11 kilonewton per meter. Then self weight of beam 25 B into D. So 0.25 unit weight of concrete into 0.23 into 0.31 is 1.78 kilonewton per meter. And then total dead load we will get 14.89 kilonewton per meter. We do not have any live load on ground beams because your live load will be on slabs, and we do not have any slab at floor level. Sorry, at ground level we can say, or ground level floor level. Then we have factorial load 1.45 into 14.89 is 22.34 kilonewton per meter, and we have this as beam with UDL 22.34, and that is 4 meter span. Then as it is simply supported, so we have WUL square by 8, 22.34 into 4 square by 8, we will get it as 44.68 kilonewton per meter. Then we have depth from bending moment consideration, and then we have design constant KU max for 0.48 because we have FE 415. For FE 250.53, FE 500 we have 0.46, and then we are going to substitute the values, which will give us RU max 2.76 Newton per mm square. And then from this we will calculate D required under root of MU max upon RU max into B. And then we will substitute the values. We will get 44.68 into 10 raised to 6 upon 2.76 into 230, which gives us 265.3 millimeter, which is less than 270 mm, which is D provided and therefore sufficient. Now we will switch over to reinforcement. As we know, formula is AST equal to 0.5 FCK upon F1 minus root of 1 minus 4.6 mu upon FCK BD square into BD. And then we will substitute the values. Mu we have 44.68 into 10 raised to 6. B is 230 and D we have small d 270 square, and same we have substituted values over here, which will give us value of AST 565.37 mm square. Now we have to provide 3 bars of 16.5 because we know for 1 bar AST for 20 mm, sorry, for 16 mm we have value that is equal to 201.06 mm square, and therefore from this we will get AST provided that is equal to 603.18 mm square, which is greater than 565.37 mm square, and therefore it's okay. Then we have check for deflection. Here I have taken check for deflection before so that we can go for shear calculations. Now DL effective upon D, we have 4000 upon 270, which is 14.81, which is less than 20. Now you try to understand, we have D is equal to L effective upon 20 into modification factor. So that means this D that is equal to 4000 upon 20 into modification factor. If you will consider 20 only, then also this value is 200 upon modification factor, means it is much less. So in beams, we are going to directly compare with basic L by D ratio. If it is greater, then we will consider modification factor and then we will calculate. If it is less than 14.81, then we need not require to go for calculations of modification factor and all this. So now we have check for development length. So we have VU. So this is maximum shear force, which is your reaction, and that is WUL by 2, and we will get this value. So 22.34 into 4 upon 2, we will have 44.68 kilonewton. Now knowing this value 44.68, we will calculate M1. What is M1? M1 is the resistance of moment or moment of resistance. Moment of resistance at support. At support. Generally, we are going to curtail 50% bar at support. 50% bar at support. And therefore, this we are not going to calculate exactly. Now you will say we have 3 bars. Then how we will curtail half? So it is considered 2 bars will go inside. So that will be greater than half of this value. And as we are going to curtail 50%, so whatever moment of resistance, that will be equal to half of bending moment at support. And therefore we have taken this is mu by 2, which will be 22.34 kilonewton meter. And then we have formula for development length, phi sigma x upon 4 tau bd. This is required value of development length. So we have substituted 5, we have 16.87 into 415. This will be stress in bar. 4, this is given 1.2, this is for M20, and 1.6 we have, that is for compression. Reaction we have, that is compression. And then we are going to get this value of LD 752.19, and we have to check it. LD should be less than 1.3 m1 upon Vu plus L naught. So this is available value, and then we will put it 1.3 into 22.34 into 10 raised to 3 upon Vu 44.68. L naught we have, that is 13 phi. And 5 we have 16 millimeter, and which will gives me value 858, which is greater than 752.19 millimeter. Therefore, okay. Then we will go check for shear. Now we have reaction at support, we have 44.68. Then we have B by 2 plus D. Now B by 2 we will have to assume. So we have considered 230 mm width of support upon 2, and small d we have 0.27. And then UDL we have 22.34. That will gives me critical shear, which will be at D from face of the support 36.08 kilonewton. Then percentage steel we will find, that is at support. So we are going to say that 50% steel will be available over there, and then we have total steel provided 603.48. And half of this we are going to consider over here, and from this we are going to calculate value 100 AST upon BD, and which will gives me value, that is 0.49, and this value I will calculate from table 19, where we have percentage steel 0.49 and grade of concrete M20, which will gives me value 0.475 Newton per mm square. Then we will calculate VUC, which will be tau UCBD, which will gives us value 29.5 kilonewton. And then we can have VUSV minimum 0.4 BD, that will gives me 24.84. And if we will calculate VURSV minimum, that is resistance due to minimum shear reinforcement along with concrete, is 54.34 kilonewton, greater than 36.08 kilonewton. And then we can have minimum shear reinforcement, that is SV 0.87 FYASV upon 0.4 B, gives us value, that is 221.92. And this we are going to provide not 6 mm legs. So we have actually this as 8 mm leg stirrups. So we have pi by 4 into 8 square, and that we will get it as 50.26. So we will have this 8 mm 221.92 millimeter. So we have 0.75D, second criteria 300, third minimum of the 3 we have this value. And then we have, so provide 8 mm diameter stirrups at 220 mm center to center. Then we are going to be with reinforcement details. So we are considering center to center 4 meter. This is 3 bars of 16 mm phi. Then we have this as anchor bars, which are 2 bars of 12 millimeter. Then we have this as spacing, and this spacing we have 8 millimeter at 220 mm center to center. If we will take section at center, then what we are going to get at this section? So I will say this as 1 1. Then we have mid section. So I will say as 1 1. So we will plot it. So we have 0.23, 0.31. Then we have these 3 bars of 16 millimeter phi, 2 bars of 12 mm tor. We will say we cannot go for tor in this, so that is shown in this. And then we have this as 8 mm phi at 220 mm center to center. So this cross section also you have to show. So this is all about your ground beams. And now we will stop here only. So thank you.